This video is for our third dynamic programming example meant to solve the 01 knapsack problem. Here's the definition of the 01 knapsack problem. The input is n items with corresponding characteristics. We have the weight of the item and the value of the item. Since we have n items, we have W1 to W sub n weights and their corresponding value V sub 1 to V sub n. Okay? And we also have as an input the capacity of the knapsack, which is denoted by capital W. So given the description of the n items and the capacity of your knapsack, find the most valuable subset of these n items such that it will fit into the knapsack, and the total value or the summation of all those selected items have a total value that is maximum. Okay, so that's the definition of the 01 knapsack problem. It's called the 01 knapsack problem because either kukunin mo yung isang item or hindi mo kukunin yung isang item. So, the naive way of solving this knapsack problem is to check all possible subset of items given n. So, the total number of the possible solution is actually the power set of n. So, yun. And the total of elements is 2 raised to n. So, bakit kaya 2 raised to n? Because I can have 0 or 1 representation for each of the n items, and 0 if hindi ko siya kukunin, 1 if kukunin ko siya. Okay, so that's the intuition how we obtain the 2 raised to n possible input, possible feasible solution for the knapsack problem. Okay, so to define the problem recursively, because this is for the dynamic programming approach, we have this definition of a smaller instance. Yung definition of the smaller instance is a subset of the items lang, which is the first I items, and we have a capacity na less than W. So we have capacity J, less than or equal to W. Okay, so to denote the optimal solution for the subset of the instances with the first I items lang and with a limited capacity J, we use the notation V of ij. Okay, so to compute for the V sub ij, we need to utilize yung solution to much smaller version of the problem, and that is V of I minus 1 J and V of I minus 1 J minus W sub I. So, medyo complicated pa siya sa part na to, pero let's try to dissect the recursive definition. Let's start with the initial conditions. Okay, so given that this is the definition of Vij, kapag I is equal to 0, ibig sabihin no items at all, regardless of the capacity, the optimal solution or the total number of values na pwede mo malagay sa knapsack ay wala, kasi wala ka namang malalagay na item. Okay? And then the second one is for this base case na regardless kung gaano kadaming items yung pwede mong pagpilian, kung wala ka namang capacity ng knapsack, wala ka ring malalagay. Okay? So that's the initial condition. And then for the recursive definition here, we have 2 cases. The main difference between these 2 cases is the condition. So, if W sub I or the weight of item I hindi kakasya sa J, then the optimal solution for this small instance is the same doon sa solution if hindi natin alam si item I or hindi natin in-include si item I. The other case is kapag kakasya si W sub I dun sa capacity J. So, if kasya si W sub I sa capacity J, we use this expression. So, we get the maximum between, hindi natin consider si W sub I, or kung i-consider natin si W sub I, yung value ni I plus yung optimal solution kung saan nabawasan na yung J natin, which is J minus W sub I. Okay? So, these two cases are the basis for populating the content of the matrix. So, just like in our previous examples, we start with the initial conditions or the base cases, and then later on, we compute for the remaining parts for as long as we can have values for this, and this. Okay. So, moving on to our example. So, let's have a knapsack of capacity W equal to 5. And then we have 4 possible items. Okay. So, for the 4 possible items, we have a corresponding weight and a corresponding value. So, for item 2, we have 1, 10, and so on. Okay. For the generic knapsack problem, sometimes we can get a portion of this item. Pero for the 0-1 knapsack problem, either we get the item or we don't get the item. That's why yung total number of feasible solution for the knapsack problem is the power set. So, this is 2 raised to 4. So, kukunin or hindi, and so on. So, for the dynamic programming approach, the way how to do it is by populating the matrix. And the definition of the matrix is this. So, remember when we defined our small instance na ang alam lang natin is the first I items and with a limited capacity J. So, the content of the matrix will be Vij. Okay, so, let's start with the initial conditions. For the initial conditions, we have the V0J, or regardless of the capacity, kung wala naman siyang items na ilalagay, the optimal total value is 0, or wala ka naman talagang malalagay. So, we have 0 here, and for the second base case, we're in if wala tayong capacity and kahit alam natin lahat ng items from 1 to let's say 4, ang sagot pa rin is 0. So, in the next slide, we can see that 0 yung column and 0 yung row. And we can populate this matrix either row by row or column by column. Okay. So, in this example, let's try yung row by row. So, ito pa lang muna, suppose yung may content. And we wanted to know kung ano yung laman ng content na to. Okay, so let's look at item number 1 with weight na equal to 2. Ang capacity natin is 1. So, using this condition, hindi kakasya si item 1 kasi ang weight niya is 2 and yung capacity ng knapsack natin is just 1. So, ang mangyayari is wala tayong malalagay, which is the value of this one. Okay, and the value of this one ay yung value nito. Okay, so we just get the value of the item above, which is I minus 1 J. Same capacity pero as if hindi natin siya nakita. Okay, so ito yung magiging value niya. That's why 0. Okay, so if we increase the capacity to 2, yan, magtatanong ulit tayo, si item 1 ba kasya na or hindi? Since the weight of item number 1 is 2, okay, kakasya na siya. So, pupunta siya dito sa condition na to. Since kakasya na siya, we wanted to evaluate this expression. Okay, so, max between this, okay, so I minus 1 J, 0, or V sub I, 12, plus this one. Okay, so Bakit kaya may arrow dito? The arrow indicates the location of this one. Okay? So, J here is 2. Our W sub I is 2. So, titingin siya sa nasa taas at may capacity na 0. So, the value of this is 0, maximum between 0 or 12 plus 0. So, we have 12. And then, let's move on to increasing the capacity. Medyo trivial tong case na to kasi we only have one item. So, kahit na lumaki yung capacity kung si item 1 lang yung pwede nating malagay, the optimal solution will be to include the item 1. So, we have 12. Yun yung value niya. Okay? And then, moving on to the second item. Suppose, nakikita na natin si item 1 and si item 2 and ang capacity natin is 1. Okay? So, in this case, ang question is, okay, let's check the weight of W sub 2, of item 2, which is W sub 2. We have a capacity 1. Okay? Kakasya na siya ngayon. Unlike kanina na hindi. So, papasok siya sa condition na to. Since kakasya siya, we need to compare yung nasa taas, that is 0, or 10 plus 0. Okay? So, the answer here is 10. And then, let's go to the increased capacity, capacity 2. And we know that we have options W sub 1 and W sub 2. So, let's ask again if W sub 2 is kakasya sa item 2. Actually, yes, kakasya siya. So, papasok ulit siya sa first condition. So, ang kino-compare niya is this one, which is this component, yung nasa taas, or if we will include item number 2, the value 10 plus I minus 1, so nasa taas niya, and the weight is 2 minus capacity 1. So, look at this position. So, 10 plus 0 or 12. So, 12 is greater than 10. And then, by increasing this further, we have capacity 3. For J equal to 3, we need to ask again if 1 is kakasya. Since kakasya siya, papasok ulit tayo dito sa first condition. We will compare if yung nasa taas niya, 12 or the value 10 plus this one. Okay? So, we have 22. So, ang evaluation niya for this is 12. Ang evaluation niya for this is 10 plus 12. Okay, so, and so on. So, ang sagot for the dynamic programming for the knapsack problem is here. If nakita na niya lahat ng items and with the target capacity. One of the advantage of dynamic programming with tabulation is that whenever there's a change in the input instance, for example, nag-change ka bigla ng capacity mo, you don't need to recompute for the optimal solution because you can simply consult this table to get the optimal solution if nagkaroon ng change. I guess that's the reason why dynamic yung name ng approach na to. Our next question is, just like in the longest common subsequence, given the answer, how can we identify the contents of the knapsack? Let's start by investigating the item in V45. So, V45. The optimal value or the maximum value is 37. Okay? So, since there is a difference between V35 and V45, ibig sabihin, we included item number 4. Okay? And if we included item number 4, the remaining capacity will be 5 minus yung weight na inoccupy ni item 4, which is 2. So, we will look at capacity 3. Okay. Our next question is to ask whether item 3 is included. Okay, so we compare again yung capacity 3 ng item 2 and item 3. So, since there is no change, ibig sabihin hindi ko siya in-include. Okay, so let's go to item number 2 and investigate if we included item number 2. So, for item number 2, there is a change between this and this, so we will include item number 2. The remaining capacity is 3. Okay, 3 minus 1 is 2, so it's time to go here sa column na to. Okay, and then let's check if item number 1 is included. Since there is a change, 12 and 0, then we included item number 1. So, to summarize, we included item number 4. We didn't include item number 3. We include item number 2. We include item number 1. So, the content of the knapsack is 1, 2, and 4. And if you get the sum, 12 plus 10 plus 15, it should be equal to 37. Yan. So, that's how you obtain the composition of the knapsack with total value of 37. Okay, so here's the pseudocode of the algorithm. And as you can see, hindi ulit siya recursive because this is a bottom-up approach. We started by populating the contents of the base cases or the initial cases. So, we have the column and the row for the stable na puro 0 lang yung content. And then for this one, we simply use the recursive definition of the algorithm to put contents of the elements here as discussed a while ago. Okay, so looking at how this is computed for the running time of this algorithm, we actually have O of n times W. Okay, so probably you would think that the running time of this algorithm is just the amount of space used, so that's n times yung capacity. But if we consider the total number of operations inside each item, this running time is actually pseudo-polynomial. So, this provides an optimal solution for the knapsack problem, pero it's in pseudo-polynomial time. Hindi siya polynomial time solution for the knapsack problem. And knapsack problem is a well-known hard problem. Since it has a pseudo-polynomial time algorithm, then it's one of the easiest hard problem. So, yun. And for the space, yes, we have O of n times capacity W. So, yun lang. Hello and welcome back. This is our second example for the dynamic programming approach. We will be solving the longest common subsequence.